Alright guys, in this video I will explain about the application of Gauss Law. Alright, in four different charges, which is point charge, line charge, sheet of charge, and also spherical charge. Okay, so first of all, let's have a big recap about Gauss Law. So for Gauss Law, we know that in terms of to use Gauss Law, we have to have a Gaussian profile. Okay, we should have a Gaussian profile. So this Gaussian profile, the shape of this Gaussian profile is depend to you. You will decide what kind of shape of Gaussian profile will be. So you should choose. It's better for you to choose, yeah, the shape of the Gaussian profile, which is the simplest shape that is easy that you can use during your calculation. All right. So let's look the first charge, which is the point charge. So let's say that we have three axes here, which is this is the x-axis, this is the y-axis, and this is the z-axis. And there is a point charge here, which is located at the origin of these three axes, which is remarked as Q. And you need to determine, let's say that you need to determine D, which is the electric field density, okay, at this point Q. Okay, at this point Q. All right, let's so now you want to use, now we want to use Gauss law. Okay, so in terms of use, in order to use Gauss law, you need to have a Gauss profile. So what kind of Gauss profile is suitable to use in this point charge? So the answer is a spherical Gauss profile. Okay, a spherical Gauss profile. So now I make a spherical Gauss profile that cross into this point P, and it is a closed shape. So now we know that the formula of this, which is D dot product ds, is equal to Q. Okay, which is equal to Q, which is the charge. Okay, and now let's look what is the direction. This D, okay, D have a direction. Okay, we know that electric field density have a direction. So the direction of D, okay, first of all, we have a Gaussian profile that the shape of spherical here. So we know that the let's say that the radius of this spherical from the origin to this point P is marked or symbolized as R. So now what is, we want to find the direction of D. So the direction of D is always normal or perpendicular with this Gaussian profile. So in that case, the direction of D will be this direction, which is normal to this Gaussian profile, right? So in that case, if you look here, that this D direction is same with the R direction here. Okay, so we can say that this D here is on the dr direction, right? D here is on the dr direction. So, and then what are the surface area for this particular spherical? I think this is come the very basic mathematics, which is 4 pi r squared, and this is equals to Q. Okay, this is equals to Q. And now we want to find, since that we want to find this D, okay, so it will be dr Q over 4 pi r squared. So since that I said that this is on this r direction, right? Same with the r direction, so it will be this Q over 4 pi r squared at the r direction. So it's very simple for the point charge. Okay, I hope you understand this one. Yeah, this should be very basic. This is very basic, where if you have a point charge, you want to find the electric field density at one particular point, for example, in this case, point P. So what you have to do first, you have to draw the Gaussian profile. So in order to draw the Gaussian profile, you have to choose a very suitable shape of the Gaussian profile. In this case, I make the shape as a spherical. So my ds will be the area surface of the spherical, which is 4 pi r squared. And in that case also, in order for you to solve the d, you need to know the direction of d, because this is in terms of vector. So now the d is always normal to the Gaussian profile shape. So now we can say that the direction of d is have a same direction with r direction, which is the radius, which is the r direction with this Gaussian profile. So that's why the vector is on the r direction. Okay, so okay, clear, right? I hope it's very clear for this point. Okay, now let's look in for the line charge here. So for line charge, for line charge, so let's say that there is a line charge here, which is on x, y, and z direction, and this line charge is placed on along along z axis, where the line charge, the value of the line charge is rho l, which is coulomb per meter. Okay, for coulomb per meter, and then you need to find the electric field density at this point P. So now, in order for us to determine electric field density at this point P, first, in order for us to use this Gauss law, okay, Gauss law, we should have a Gaussian profile. So what are the shape of the Gaussian profile that is suitable in these cases? So the shape of the Gaussian profile should be a cylinder shape. All right, so this cylinder shape has a height of L, which is a finite height, which is I represent it as L, and the radius is R radius, okay, which is from this origin, which is from this z-axis towards this point P, which is on the R direction. The radius is R. Okay, now we need to find what are the direction of this T. Where is the direction of this D? So the direction of D, I always say that it is normal to this Gaussian profile. So the direction of this of D will be at this direction. So in this case, we can see that the direction of D is same with the direction of R, right? The direction of D is same with the direction of R. All right. So if you still remember, I have explained in the tutorial yesterday. For this cylinder, there are actually three surfaces. 1, 2, and the one that which is on the bottom here, which is 3 surfaces. So since that our formula that we're gonna deal with is equals to Q, all right, D. So D here is there is a possibility that D exists in surface 1, 2, and 3. So D here will be the sum of surface 1, 2, and 3. So now S1 D ds1 plus d, okay, this is all vector, yeah, s2 ds2 plus d on ds3, right, which is on s3 here. Okay, so now let's look one by one. So since our d is on a dr direction, so our d will be dr on the r direction, yeah, always, yeah. So s1 you can see that now it is same direction with, because it is moving upward, right? So it is same direction with z here, so it will be r dr dphi on a z direction. So in this case, we can see here that there are the dot product, the direction of this dot product is different direction, and in orthogonal coordinate system, all the direction is normal to each other, right? Which is 90 degrees to each other. So we can say that this will produce you 0, and this will give us 0. Okay, so there will be no z component here. There will no electric field density at this component here. That's surface number 1. How about surface number 2? Okay, so the surface for surface number 2, let's use different ink. But this d is same, yeah, on r direction. However, for this surface number 2, s2 will be the direction of S2 is same as radius, right? The radius. So it is on the r direction. So it will be r dr dphi on r direction, right? R dr dphi on r direction. Okay. Sorry, r dphi dz. Sorry, this is dz. This is supposed to be dz. Yeah. This is supposed to be dz. So sorry about that. Okay, this is supposed to be dz because this is on r direction. So in this case, you can see that this what dot product, they have same direction. So dot product same direction will give you 1. Okay, so this will not be 0. How about for surface number 3, which is down here, located at down here? So surface number 3 is actually same as surface number 1. However, the direction, the difference is only the direction because the direction is going downward. So it will be dr, r direction. So this is going to be r dr dphi on the z direction, and since that you can see here there is a different direction, and automatically it will be 0, right? So this will be 0 as well, and it will leave behind only this part. So it will be, for this terms, yeah, for this term it will be d, right, as ds, where it will be d, which is this here, d, and our ds is going to be r d, I forgot to write the integral. Okay, it will be this part, yeah, integration dr integration of r dz dphi, and this part, okay, in this part it will be, if you solve here, there will be dr r z is what is from 0 to l, right? 0 to l dz, p is what, 0 to 2 pi of phi. Okay, and here it will, you will get that dr r l l, this dr is r direction, yeah. I think it's better for me to write, if not we will confuse. It will be dr here, yeah, and then r, which is here, l, and then 2 pi. So the result, this is the result for this part, which is on the left hand side part. How about the q here? So q will be, this q will be what? Will be the total charge for this line of total charge for this entire our Gaussian here, which is on the enclosed here. So it will be rho L. Okay, rho L, since that the component that we that will be that we will use is only this component number 2. Yeah, it's on the r direction. So rho L be L. Okay, rho L L. So the total, okay, the final, it will be dr r L 2 pi is over rho L, is rho L here, yeah, and then the length here L. So in order, since that we want to determine D, so D will be, our D here will be, okay, will be, this L can be cancelled to each other, so it will be rho L over R 2 pi. Okay, so this will gonna be our D. Alright, so I hope this is very clear. Yeah, the Q here is Q enclosed. What does that mean? Q inside this particular cylinder. Okay, Q inside this particular cylinder. So since that this cylinder what since that this cylinder, the one that we determine is only uh, on the surface number 2, so the charge that contains here will be rho L. Okay, rho L. And don't forget that since that this is vector, I forgot to write the direction, so the direction is on a R direction. Okay, so this is for line charge. Alright, so now let's look at point number 3, which is sheet of a charge. Okay, let's discuss a sheet of a charge. So now we have a sheet here, which is lies on the XY plane, and the Z plane is equals to 0. Okay, so it lies on the XY plane and independent from Z axis. So what you need to do is you need to determine the D at this particular point P. Alright, so now in order for us to use the Gauss law, okay, in order for us to use the Gauss law, we need to draw or have a Gaussian profile. So the best Gaussian profile shape for this point P, and based from this particular sheet of charge, will be a rectangular, which or a cubic. And this is a cube of a point of Gaussian profile. All right, so this cube, I put that the area, okay, the area of this cube is A meter squared. So we know that the D dot product with the S area is equals to Q enclosed. Okay, so first we need to find the D. So where is the direction of D in this particular based from this shape? Yeah, so the direction of D is always normal to this Gaussian profile. So D is possible to exist on the top and also at the bottom of this particular Gaussian profile shape. So it will be, the DS will be, okay, now in this case here, our DS will be D, okay. So now this is more becomes DZ, yeah, because it is same as a Z direction, okay, and DS, all right. So this DS is the surface area at the top and the surface area at the bottom, right? Because it is possible to exist at these two directions. So DZ, okay, and the surface area, which is surface area at the top plus, DS plus surface area at the bottom, DS. So it will be, all right, so this integration will give you A, and this also integration will give you S, which is surface, yeah, surface is A, and then A, because I said that the area is A, so I just put it as A here. So it will be DZ to A. So this is for the left hand side. How about the right hand side? For the right hand side, the Q, which is Q that contains inside this particular Gaussian profile, so it will be rho S, okay. So for here it will be rho S, so at this particular surface, right, ds, and this will give you rho S A, right, rho S A. Okay, now we need, since that we need to determine Z, okay, in order to determine the Z, which is at Z direction, right? So this is at the Z direction, okay, Z at Z direction. So it will be rho S A over 2A at Z direction. So it will be D, it will be rho S over 2 at Z direction. Okay, so I think this is very easy, right? So the how to make the calculation, our calculation simpler, is based on our Gaussian profile shape. So it's very important for you to determine what shape of your Gaussian profile. Okay, what shape of your Gaussian profile. Okay, so now let's proceed with the another charge which is uniformly charged sphere. So in this case, I have a sphere which I draw in 2D. Okay, so this is a sphere where it has a radius of A, and the charge density is rho naught coulomb per meter cubic. All right. So what you need to do is you need to determine D everywhere in this particular shape. All right, so now in order for us to determine D everywhere in this particular shape, we should have visualize where is the D that possible to be exist. So D now possible to be exist inside the sphere and outside the sphere. So now let's consider that D is located inside the sphere. So I make it a point P which is located inside the sphere, and I should draw my Gaussian profile which is based from this point P. So my Gaussian profile by right, okay, by logic should be same with this sphere shape, which is sphere as well. So my Gaussian profile now, I make it point P is here, so it has a radius of R, which is based on this point P, and it can be variable, when I change this point P. So it will be different if I put my point P here. R will be based on this point P. Yeah, and I make a true condition for this region 1, which is I make that my solution, okay, is true when it is R equal and lesser than A. Okay, I also can make my R is lesser than A, so it's depend. So you the one who should make this limit. Okay, this true condition. So I make my condition R is lesser and equals to A. Okay, so in this region 1, okay, I make my calculation. So based on this particular Gauss law, all right, is equals to Q enclosed. All right, so this ds, think, all right, ds, I think by now you already know that where is the D direction. The D direction is normal to this Gaussian profile, so it is same with this R direction. Yeah, so it will be dr, okay, dr, and ds here is the surface area for this Gaussian profile, so it will be 4 pi r squared, which is r, this r, which is referred to this r. And for this Q enclosed, okay, for this Q enclosed, so the Q that is contained inside this area, okay, Q that contained inside this area, so it will be Q, which is the volume inside this area, yeah, rho V over times with dV. So rho V, we know this is the value of the charge, will be rho dV, and this dV is based on our sphere shape, which is r squared sine theta dr d theta and dphi, right? Dphi. Okay, so since that it has three variables, okay, since that it has three variables, so it will be okay, so since it has three variables, so it will be rho v 0 until r, since that I make my limit here is r, yeah, 0 until r, okay, 0 until r, so r squared dr, and then theta 0 until pi sine theta d theta, and then the one for phi 2 pi this the phi, and this will get, okay, this will give to me, okay, this will give to me rho 4 over 3 pi r squared. Okay, so now since I know that this is dr for pi r squared, this is rho not 4 over 3 pi r squared, I can find my dr where in these conditions, right? So now my dr will be 4 over 3 pi r squared over 4 pi r squared. So it will give me rho mu this is r cubic. So this is r cubic, sorry, this is r cubic. Okay, so because r squared differential, it will be r cubic. Yes, this is going to be r cubic. So this will be r, yeah? So this will be r over 3 over 3. Okay, in r direction. However, this condition is applicable when this r, what is the range of this r? What is the range of this r? My range of r, since that I make my range of r is r is lesser than a, so it can be, there is a possibility of this limit of r will be must be bigger than 0. It cannot be 0, okay, because if it is 0, it will be 0, right? 0 uh, bigger than 0. Okay, r should be bigger than 0. However, it should be same and lesser of a. So this is going to be my r, the range of my r. Okay, the range of my r, because I make it r is lesser than a. But if I make it r is lesser than a like this, my range of r will be 0 r a, right? Is that, are you agree with me? Okay, it will be like this, right? So it depends on what is your range of here that you have set here. Okay, so this is when r is lesser and equals to a. How about, okay, how about is r is bigger than a? So now let's consider that I have another point, which is point P here now, okay, which is outside the sphere, and I want to find the electric field density. So I make another circle which is across this point P, okay, and now I have a new R. Okay, I have a new R, which is R here is larger than or equals to A. R here is larger than or equals to A. So my R, this R and this R, the R that colored in the green color is not same. The value is not same with R which is represented in blue color. It is different R. Okay. So in this case, so I don't have any much more space. I should write it. Shall I write it here? I should write it here. Can I have? So where suppose I write? Can I erase this part? Okay, so I will put it here. So I will write it here. Yeah. So when R is this, oh, I should write it in blue color. Wait, yeah, I write it in a blue color. The answer here, I will write in a blue color here. I will write in a blue color here, where my R, dr is rho not r3 and r direction, where it should meet this condition, yeah, 0 r a. Okay, so now allow me to erase this part because I don't have any much more spaces. Okay, but I will lift this formula because I'm going to use the same formula. All right. Okay, now, so my d, okay, so for the left hand side, it will be same, right? For the left hand side, it will be same where dr, this is based on my experience here, you will get dr, and then the ds is 4 pi r squared. How about the right hand side? So now for the right hand side, okay, for the right hand side also, actually it will be same. Okay, it will be same since because the formula is rho v dv, right? And our rho v is same rho naught, and this is same with this one, and it will give you the one that I have calculated earlier, which is 4 over 3 rho naught pi. What the difference is now, my r, yeah, okay, my r here will be different when r is equal, is larger than a. So my r here, allow me to write it again. Yeah, allow me to write it again. I will, and so it will be r squared sine theta dr d theta dphi, right? So to use this part as well, okay, so it will be r squared dr 0 until a, okay, because this is the charge that contains inside this, when the charge that contain when the electric field density is larger than a. So there will be no charge exist at this point, right? There will be no charge exist at this point. Charge can only be exist inside this particular sphere. So that's why my range is 0 to r instead of 0 to a instead of 0 to r. Because why? Because the limit of the charge to exist is only on this particular object in this particular area. So that's why the limit is 0 until a only for the charge to exist. So instead of r, I put it as a. Okay, I hope that clear. Okay, and then this is going to be pi, sorry, this is going to be pi, okay, sine theta d theta, and then 0 until 2 pi for d phi. So in this case, right, it will be rho naught 4 over 3 pi a cubic. Okay, instead of r, it will be a cubic, and then dr will be 4 pi r squared, and in order to find dr, so it will be 4 pi can cancel to each other, so it will be rho naught a cubic over 3r squared at the r direction. This is our dr. Okay, so the dr, so what is the condition or the limits for this one? The limit is r should be larger or equals to a. Alright, so be careful here. Okay, be careful here. Okay, be careful here at this point. Okay, for this part, yeah, when r is larger than a, okay, the charge that contained is not will be entire of this area. The charge that contained will only entire of this object only. No matter how big the Gaussian profile will be, the charge will only contain inside that particular sphere only. Okay, because they said inside this equation that the charge that exists inside that area is rho naught c meter cubic. So other than that, it will be 0. So that's why the limit for that charge, although that the Gaussian profile is bigger, is larger, the limit for the charge to exist is only a until a, or 0 until a. Okay, so the d, or the d that will exist is rho naught a cubic over 3r squared at r direction. Okay, so I hope this is very clear for you. Please make yourself very clear for this part, because this will come up inside your test. And then if from here also you can draw actually the charge distribution. Okay, you can draw the charge distribution when this is axis, yeah, r, and this is the charge distribution or the charge density. Okay, so this is from 0 to a. When radius is 0 to a, what will happen to the charge? What will happen to the electric field density? You can see that the bigger the radius, yeah, the bigger the radius, the more the electric field density will be. So it will be linear. but there is a limit. The limit is until A. When it is after A, what will happen is if it is after A, you can see that when after A, the larger the radius, the smaller the electric field density will be. So it will be decreasing. Okay, this is going to be decreasing. Okay, so if the question asks you to draw the or sketch the electric field density distribution, so this is how the distribution will look like. Okay, right. So I hope this is very clear for you. And from here you can see that this is from the last tutorial question, where some of you questions about the what is the range of this? How about the range of this, right? Where it is supposed to be like this, or it is supposed to written like this. It is up to you actually. So if you write it as R is lesser than the R range here, so when the Q enclose here, yeah, Q enclose here, so Q is the one that you put here is only considered inside this particular region. So the R when it is lesser, so when the R is lesser than R small letter is lesser than R capital letter. So the Q that enclosed is only Q that enclosed in this particular shape. So the limit of R is 0 until R. Okay, there's nothing to do with this range. Okay, there's nothing to do with this range. All right. So the R, but what are this to make this one is true is R here. Okay. So you also can write R equals to R. It depends to you. Okay, it depends to you. When you write R lesser than R, the range here also will be 0 until R, because this is the one that you put the point. The Gaussian profile is located lesser than R here. Okay, but you need to put the range here at your final answer. You put your range where R is at this condition. Okay, however, for when R is larger than R, when this R is larger, sorry, this is supposed to be R2, yeah, R is larger than this R. Okay, your what your charge that will exist is only it will be two parts of charge that will exist. One, the range is when the 0 until R, where the value of the charge distribution is rho naught R over R. Okay, rho naught R over R. So, which is on this part. And then another part is from this R, okay, from this R, if to this R, from here to here, which is from this R to this R. So the value of the charge distribution is 0. Right, the value of the charge distribution is 0. So this will gonna give you 0 actually. All right. So it will leave you only here. It will leave you only 0 until R. So what does that mean? It means that charge is only contains inside this shape. There will be no charge contains inside this. Okay, and this you will get, yeah, you will get your answer is this for your answer. And this for your answer, the range is true when R here is larger than R. Okay, right, I hope you can also make like this, yeah. I think this is the sign here is not so important. The most important thing that you need to define the range is at this particular Q enclosed here. Okay, where is the range of the charge exists? 0 until R, because when 0 until R, there is the charge distribution value. However, when from this particular part to this particular part, the value of charge distribution is 0. So this is going to be 0. So if you take a wrong range, for example, if you take 0 until R here, okay, you might have a different answer, and it will lead to you, it will lead your answer to wrong answer. Okay, so you have to be very careful at this particular part. Like I am not too worried about this left hand side, because left hand side I think you are already clear. Only the right hand side. Okay, be careful about the range of the charge axis. Alright, so I hope this video will make you more clear about the charge, about the Gauss law, the application of Gauss law. So if you have any questions that you want to ask, please let me know. Okay, and I hope you do your revision before your test. Yeah. Thank you so much. Assalamualaikum.